Hey guys, I wanted to give a follow-up lesson to what we talked about earlier this week. In the last couple lessons, we've talked about solubility, about how much something will dissolve, and we've gone through and we looked at some solubility charts. We talked about how temperature has a big effect on how much of something you can dissolve, especially with things like nitrates and sugar. Temperature has a really big effect on that, and how gases kind of have the opposite trend, how heating up a substance makes a gas come out of solution, so less of it can dissolve. And we can remember that with soda pop. When you heat a soda pop or heat up any sort of fizzy drink, all the fizz comes out because the gas can't stay dissolved. And we talked about this with some other things that this has an effect on. The last thing that I want to do for the whole solutions chapter is give you an introduction to how you can calculate how strong a solution is. Everything that we've done up to this point, we just kind of talked about how the weight of something that you dissolve. But probably one of the most important things to take forward into your college chemistry classes or even into any sort of medical field is to understand some units for concentration and to kind of understand what that signifies. Um, so we're not going to do this part that says colligative properties. I think is for the sake of time. I think that we have some things in acids and bases that'll be important to get to. So we're not going to do colligative properties, but we are going to talk about concentration a little bit. So concentration is basically a simple way of saying it is how strong a solution is. Concentration has to do with how much of something you have dissolved in a given amount of solvent. So an example I like to think about this is if you have laundry detergent, lots of times it says there's twice the strength of the laundry detergent. And the reason this is like this, how can they advertise something as being twice as strong? Well, really, what you're buying when you buy laundry detergent, a lot of it is water. And so when you're buying a gallon of detergent that says 2 times the strength of regular all, what they're doing is saying that you have the same amount of actual soap and fragrances or whatever as you do in 2 bottles, because the rest of these bottles are just water. These are more watered down, or they're more dilute, we'd say. So the opposite of concentrated is dilute. And usually what that means is that you have more water, or you have some more of some other solvent in there and not the active ingredient that's dissolved. In chemistry, there's really 3 important units for concentration, but we're really just going to talk about one of them. We're going to talk about what's called molarity. Molarity is, you see the word mole in it right away. Molarity is a way of measuring concentration by moles. So how many moles do you have dissolved in a liter of solution? This is actually a really important unit because it means that you can measure a number of molecules if you know the volume of something. So you've seen these before in the chemistry lab because I've often given you compounds that are labeled like 1 molar solution or 0.5 molar. A molar is a pretty strong concentration. If you have an entire mole of something dissolved in 1 liter, that's actually a pretty strong solution. There's something similar to this called molality, which we really only use to talk about things changing temperature, because so we're not really going to spend a whole lot of time on molality this year. I'm sure you'll get to it in your college chemistry classes. It's molality and molarity come out to be almost the same number, but when you heat something up, the size of a liter kind of changes. So like if you have a liter of water at 4 degrees Celsius and then you heat it up to 10 degrees Celsius, it's actually going to expand a little bit. So the size of it will be different. So the molarity would change, but the weight of the water doesn't. So that's the only reason anybody talks about molality. So we're just going to focus all of our attention on molarity in this case. So molarity, we always use a big M. So molarity is the number of moles you have dissolved and divided by the number of liters. So sometimes I draw this as a triangle just because it makes it a little bit easier to remember. We did this a lot freshman year, some people liked these, these little triangles, we can say. So we can say molarity is moles over liters. And remember that moles aren't the same thing as grams. Do you remember? We can do a little refresher on how we calculate moles. You can always divide divide a mass of something, a number of grams of something, by something's mass on the periodic table. Okay, so that's how you get from, so to get from grams to moles, you always divide by the molar mass. Okay, so just as a reminder, we haven't done that in a while. Okay, so I'm going to do 2 example problems. There's really only two different things that you ever need to calculate with this. You could be given a number of grams and you need to calculate a strength, or you're given a strength of something, a molarity, and you need to calculate a number of grams. Now, usually getting grams isn't one step because you have to find moles first. So let's do an example here. So the example is, what is the molarity of a solution composed of 5.85 grams of potassium iodide, Ki, gives us a formula, dissolved in enough water to make 0.125 liters of a solution? Okay, so we think about what we know and what we don't know. So do we know molarity? Do we know moles? Do we know liters? 5.85 grams is going to help us figure out a number of moles, but it is not a number of moles. So, but we do know a number of liters right off the bat. We know that it's 0.125 liters. Okay, and the molarity is the unknown here. It says, what is the molarity? So that's what we want to know. But before I can figure out a number, before I can just plug things into my formula, the M equals moles over liters, before I can just plug things in, I need to figure out how many moles of potassium iodide I have. So for that, I go to my periodic table. Potassium is 39.098. Iodide is 126.904. And that comes out to 166 even, 0.00 with rounding. Okay, so 166 grams per mole. So I need to get the molar mass, or to get grams to moles, I take 5.85 and I do grams times 1 mole over 166. That's 0.035 moles. Sorry, it's hard to write with a mouse. So 0.035 moles here. So 0.035 moles, so to calculate the concentration, I do 0.035 moles divided by the number of liters. So that comes out to 0.28. Molar is the unit for that. So the answer is this divided by this. That's what the whole triangle I was trying to draw. So if I'm looking for molarity, you can kind of cover that part up and say, oh, what's left over is moles over liters. Okay, so I want to do another example where we're going sort of the other way, where the number of grams that we would need is unknown. So in this case, we have to sort of start knowing a little bit about the solution and sort of working our way backwards. So this says how many grams of H2SO4 are present in 450 milliliters of a solution that is 0.150 molar. Okay, so in this case, we'll kind of think about what we know and what we don't know. So in this case, we know the molarity is 0.15. We know the number of moles. Well, actually, we don't know the number of moles. That's what we're going to have to find first. And we know the number of liters. You'd think it's 450, but it's not. It's 450 milliliters is less than half a liter. So it's move the decimal 3 places to go from milli to liters. So it's actually 0.450 liters. Okay. So how do I get, if knowing the concentration and the number of liters, how do I find a number of moles? Okay, so, well, let's look at the little triangle here that we just drew. If I don't know the number of moles, that should be molarity times liters, right? Like if moles were unknown, I would have to multiply both sides times liters, and it would be liters times molarity. Okay, so the number of moles should be equal to the molarity times the number of liters. Okay, so in this case, it would be 0.150 times 0.45. So that comes out to 0.675 moles. But that's not what the question is asking for. The question doesn't want to know how many moles of H2SO4 we have. It wants to know how many grams of H2SO4. So we have to convert moles to grams here. So we're going to have to use this number of moles, but we're going to need to know the molar mass of this. So you have to add up 2 hydrogens, a sulfur, and 4 oxygens. This is one I know kind of off the top of my head because we work with it all the time. So this comes out to 98.08 is the molar mass of H2SO4. Okay, so am I going to divide or multiply? Well, if I'm going moles to grams, I have to multiply. So if I want to know the number of grams, that should be 0.0675 moles times, scroll down a little bit, and that would be 98.08 grams in 1 mole, right? For those of you that like to set up your fractions that way. So I'm multiplying this times 98.08. That I don't know off the top of my head. So, oops. So this comes out to 6.62 grams. I would need of H2SO4, sulfuric acid. So in this case, I took the number of moles in liters and worked my way backwards to find a number of moles, and then take that to a number of grams using the molar mass.